Hello everyone. Today we begin our discussion of transformations, and we start by looking at transformations in two dimensions. So what is exactly a transformation? A transformation can be thought of as a mapping from one vector space to another vector space. That is, given vectors from one vector space, it maps these vectors to vectors of another vector space. Now you should know what is a vector space. In case you need to revise this concept, please go back and read up about it. Why are transformations useful though? Transformations are used in graphics for two primary purposes, both modeling and viewing. So modeling involves moving objects around, changing their orientation, changing their size and scale. This helps us create multiple instances of template shapes during modeling. For example, you might have one template model of a chair, and you can create multiple copies of this at various positions and orientations by using transformations. Modeling transformations also allow us to make hierarchical models. These are basically models where the parts of the model are related to each other by a hierarchy of transformations. We will see hierarchical models in a later lecture. Then remember our synthetic camera model, which is the pinhole camera model that we introduced in the previous lecture. We still have to simulate the imaging process using that camera model, and we will see that that is done by specifying what is known as a camera or a viewing transformation. So how does all this fit in together? They fit in together into what is known as the modeling viewing pipeline. So this is the abstract view of the pipeline. Given a set of objects in their own respective coordinate systems. So for example, imagine that you are modeling a table and two chairs. So let that be model 1, 2, and 3. And they have been created in their own respective coordinate systems, and these are known as model or object coordinates. So now they are all placed in a common 3D world, and the transformation that gets them from their local object coordinates to world coordinates are known as modeling transformations. So M1, M2, M3 in this case are modeling transformations. So once you have all these objects into a common 3D world, then they form the part of your virtual 3D world, and their coordinates and vertex locations and the geometry can be viewed in the terms of world coordinates. Once you are in the world coordinates, now you can start to set up your viewing transformation. So if you go back and look at the pinhole camera model that we talked about in the previous lecture, you will notice that we said the camera center was located at the origin. However, when you are taking pictures in the real world, your camera is in your hand and you are pointing it towards the object, right? And wherever the camera is, that point need not be the origin of your world, because when you created your world by placing objects in it, you just chose an arbitrary origin. That was not the center of the camera. So how do you use the camera coordinate system that you set up in the previous lecture and use the pinhole camera model if the coordinate system is different? So we say that in world coordinates, the origin can be anywhere, and in that coordinate system you specify the position of the camera center. So you specify it in world coordinates, and then you set up a independent coordinate system using the look at vector, the up vector, and the third axis of the camera coordinate system, and then you apply a transformation such that the origin of the 3D world transforms to the camera center, and the axes of the 3D of the world coordinate system transform to the axis of the camera coordinate system. And the transformation that does this for you is known as the viewing transformation. So do not worry if this seems a bit confusing at the moment. We will look at this in greater detail when we start to actually develop the viewing transformation and try to figure out what are its details. For now, it is enough to understand that any geometry that you specify in your application program has to undergo this process before it finally gets displayed on the screen. So you were in local object coordinates, then the objects got transformed using modeling transformations, and they landed in a common 3D world. From there, you apply a viewing or a camera transformation so that the coordinate system of the 3D world aligns with that of the camera coordinate system. And now you are still in 3D, but just to distinguish between the earlier 3D and this 3D, we are calling this the 3D scene, and the coordinates are now called the camera coordinates or the view coordinates. So viewing transformation, camera transformation means the same thing. Similarly, view coordinates and camera coordinates mean the same thing. Now, after the 3D scene, we apply what is known as a projection transformation, and using the projection transformation, we drop from 3D to 2D. Once we have the 2D scene, we are ready to pass the 2D scene to the rasterizer. So this is the portion of the pipeline that we have seen actually so far. We have seen how to rasterize, and we have seen how to clip in 2D. So the 2D scene is passed to the rasterizer, and then clipping is performed, and that gives you the final 2D image that you draw to the screen. Okay, so we have seen this part of the process, and what we are going to talk about now will actually let us figure out how to do modeling transformations and how to sort of compose these transformations so that we can create this 3D world. Okay. Today we are going to only talk about 2D transformations, or when the objects themselves are in 2D in the beginning, and how to compose them on the 2D plane. But after this, we will talk about 3D transformations. So there are just some concepts that are easier to introduce in 2D. So once we are familiar with them, we will move on to full 3D modeling transformations. And then once we are familiar with the various kinds of modeling transformations, we will look at viewing transformations and projections. So let us get right into it. First, I want to introduce some notation. We will represent vectors. So suppose you have a vector u, which you would normally say if ux, uy, uz are the three components of u along the three axes. Then we are going to write u as a column vector. So we are going to represent, since our transformations are going to be matrices, and we want to apply these transformations to vectors. So vector is going to be a column vector. So that is the choice we have made. And now, given a transformation T, we apply this transformation to a vector u by pre-multiplying the transformation to the vector, and that gives us a transformed vector. So here, of course, this is any vector from a given coordinate system, and this is a general 3x3 transformation. We will talk about what these quantities, what do they represent, and what is the geometrical interpretation of particular transformation in the coming slides. So let us start with the simplest transformation in 2D. So a point, say you're given a point px, py. So this is a vector or a point in 2D, and you want to apply to this what we call as a scaling transform. So a scaling transformation in 2D is represented by this diagonal matrix. So there are the diagonal non-zero entries Sx and Sy, whereas the off-diagonal entries are all zeros. So if you apply this, you get the transformed point P prime. So P prime is S times P, and that gives you this transformed point once you apply the transformation to the original point. So now if I want to transform a shape, so for example, let us imagine that you have this unit square, right? So given this unit square, you want to transform this unit square using this scaling transform, then the way to do it is to apply the scaling transform to each vertex of the unit square. So the unit square might have 4 vertices A, B, C, D. Then you apply the same scaling transform to all the 4 vertices, and you get A prime, B prime, C prime, D prime as the transformed shape. Okay, so please remember this, that whenever you are transforming a shape with a transformation, and this applies to all transformations, you apply the same transformation to all vertices. Okay, otherwise you cannot talk about the effect of that transformation to that object. So you apply the same transformation to the vertices of an object if you want to compute the effect of a transformation on that object. Okay, this seems obvious, but still people tend to make mistakes, so do remember this point. So now, depending upon Sx and Sy, different things happen to the square. If Sx is equal to Sy, you get what is known as uniform or isotropic scaling. That means the scaling in the x direction and the y direction is the same. So a unit square might become a bigger square, but it will stay a square if you apply uniform or isotropic scaling. However, if Sx is not equal to Sy, then a square can change into a rectangle, and in such a case, the transformation is known as a non-uniform or anisotropic scaling. Right? So scaling does not disturb the angles inside the square; they stay right angles. However, the length of the sides, those can change depending upon the Sx and the Sy. So the y length change according to Sy, and the x length change according to Sx. Right? And the reason for that is the way in which matrix vector multiplication happens. So Sx will go and multiply with Px, and Sy will go and multiply with Py to get P prime x and P prime y. So this is scaling. The next most common transform is rotation. So what we can think of is that given rotation about an origin O, right, we might want to rotate a point P to a point P prime. Okay, and we want to figure out the matrix transformation that will do this for us. So imagine that the point P was at this angle phi. So if I take the vector OP, okay, then I can write the coordinates of point P as r cos phi and r sin phi, where r is this distance. Okay, and now I want to rotate P to P prime, and P prime is a further theta rotation from OP. So OP prime is obtained by rotating OP by an angle theta about O, right? And notice the sense of this rotation. This rotation is in a counterclockwise direction. So that is what we are considering as positive rotations. Okay, so that is just a MAC convention. That is the convention that we have chosen, that counterclockwise rotations are positive. So now, what are going to be the coordinates of P prime? P prime is r cos phi plus theta and r sin phi plus theta. You can apply trigonometric identities to expand cos phi plus theta, and sine phi plus theta to get this. So you want a matrix transformation that is going to transform P to P prime, right? And simply by inspection, you can figure out that this matrix has to look like this. Okay, you can verify, you can multiply this matrix with P and see that you get this P prime. Okay, so R theta, which is rotation about the origin. So remember that rotation is always about something. So in 2D, rotation is about what is known as a pivot point. So pivot point. Okay, so the default pivot point for rotation is the origin. So R theta gives you theta rotation in the counterclockwise direction about the origin, and the matrix is cos theta minus sine theta cos theta. Okay, and we just now saw the derivation. The derivation is by construction, and it should be pretty simple to understand. Okay, so if I rotate a square, it will stay a square. Its size will not change. So the length of the sides do not change. The angles inside the square do not change. Just the orientation of the square changes. Now let us look at the transformation, 2D transformation in general. So we might have a transformation that is ABCD. If that is the case, then we get the transformed points as A times Px plus C times Py and P prime y as B times Px and D times Py. Depending upon what values you give to ABCD, you will get different transformations. If T is an identity, then nothing happens to Px, Py. That is just known as the identity transformation. If, however, I make B and C 0, then we get the scaling transformation. This is something that we have already seen. If I make A minus 1, D1, and B0 and C0, then Px just changes to minus Px on multiplying with this matrix, and Py stays the same. So this is like you have the coordinate axis, right? And suppose, let me make a shape here. We have a shape that looks like this. Okay, and this just changes to a shape like that. Yeah, so A, B, C will map to A prime, B prime, C prime. Okay, so the x coordinate became negative and there was no change in the y coordinate. Okay, so this is reflection, right? Like rotation, you can see that reflection does not cause any change in the size or the angles of the object or the shape that you apply it to. It is just that it is placed differently on your 2D coordinate, on your 2D plane. Okay, so this particular transformation is reflection about the x is equal to 0 line. So this is the x is equal to 0 line or the y-axis, right? Similarly, you should try and construct reflections about the y is equal to 0 line or the x is equal to y line. You should be able to make those transformations by yourself. So this gives us a sense of what kind of transformations are possible in 2D using 2x2 matrices. Okay, so there is just one more transformation that we need to talk about in 2D, which is shear. Okay, so what happens if I have ones in the diagonal and non-zero off diagonal terms? So scaling was the opposite. It was non-zero diagonal and 0 off diagonal. Now we have ones in the diagonal, so the diagonals reproduce the same point, but we have non-zero off diagonal terms. So once you have that, so suppose you have this C here, okay, in the upper right, then you can see that P prime X turns out to be px plus c times y. This is very interesting. You find that the x coordinate is being changed by a multiplicative scaling of the y coordinate. Okay, so this kind of a transformation is known as a shear, and this particular shear is a shearing in x direction. So the points in x, which are like these points, they move to along the positive x-axis, right? And the movement in x is proportional to the y coordinate. So if so the origin did not move at all, you will see, right? Because the y coordinate is 0. So if I just label these points as A, B, you can see that AB did not move at all. A prime, B prime are the same points. Okay, and then C prime and D prime, however, have moved, and the amount of movement that happens is proportional to the y coordinate of that point. Okay, so this is shearing in x. You can similarly imagine that you can have a shearing in y if you have this as non-zero and this coordinate as 0. Now, so this is shearing in y. There is no reason why one of these should be 0. You can have C and B here, both of them non-zero. Then you will have general shearing in the 2D plane. Okay, so I just showed you shearing separately in y and x to give you an idea of what shearing is all about. But you can have general shear in the 2D plane. Okay, so when you are shearing in y, the y coordinate changes as a multiple of the x coordinate, right? The offset in y is a multiple of the x coordinate. Okay, so that was shear, right? So now we have seen transformations like scaling, reflections, rotations, the identity transform, and shear. Okay, so these are all 2x2 transformations. Another very common transform is translation, and you might be wondering why haven't we talked about translation at all. That is because translation is kind of an odd one out. Okay, so if you think about what translation does, translation might take a shape ABCD and move it, right? So the orientation of the object did not change. The size and the shape of the object did not change. It just moved. So the movement was like a shifting of the object, right? And no matter how hard you try, you will not be able to represent a transformation as a product with a 2x2 matrix, like we have been able to do with the earlier transformations. The easiest way to represent translation seems to be to just add a offset vector. So if P is your original point and P prime is the translated point, then from P prime to P, you just have to add a offset vector, which is this Px Py. And this seems to be very, this seems to be very odd, and it is not that good, because suddenly here is a transformation that you cannot perform using 2x2 matrices. And we would like to be able to do all our transforms using the same kind of mathematical operation, because we want to be able to apply transformations really fast. Okay, because transformations have to be applied to, say, all vertices of your world repeatedly. So transformations better be accelerated using hardware, and they better be the same kind of operation, because then it is just easy to again and again call that hardware instruction. If you suddenly have to do something else for translation, and I'm not saying that vector addition is a particularly difficult thing to do, but you have to figure out that you are trying to do a translation, okay, and you have to do something else for that. So just figuring out if your transformation is a translation, then do something else. This if then else kind of a logic is something that you do not want in something that you want to run very fast. Okay, so is there a way of representing translations in a manner such that they can also be performed using matrix multiplication? Is what we will look at in the next set of slides. Okay. However, before we go there, I want to introduce this concept of a linear transformation. So we all understand that translations are different, but let us try and understand why and what is different about them. Okay. So given two vectors u and v from a vector space capital V and a transformation T that is a mapping from a vector space V to a vector space W, this transformation T is a linear map if and only if it satisfies these two properties. So the first property is that the transformation applied to the sum of two vectors is the same as the sum of the transformed vectors. And two, the transformation applied to the scaling of the vectors, so alpha here is a scalar, is the same as the scaling of the transformed vectors. Okay, so if a transformation satisfies these two properties, then that transformation is a linear transform. Right? Now, if you understand these two properties, what I want you to do is to prove the following. Take all these transforms that we could represent as 2 cross 2 matrices, which is scaling, rotation, deflection, and shear, and prove that they are all linear transforms. So for that, you will have to take general forms of these transformations, and you will have to take a generic point in 2D and show that take two generic points in 2D, u and v, and you will have to show that they satisfy the properties that we mentioned here, right? So both 1 and 2. And then I want you to show that translation is not a linear transformation. So if you apply transformation by adding a offset vector, and that is the map that the translation transformation does, that it adds an offset tx by to any point in 2D, then that operation does not form a linear map. Okay, so I want you to prove these two things, and that should tell you why is translation different, right? So translation is not a linear transformation, and that is why we are unable to represent it as a 2 cross 2 matrix in our normal 2D Euclidean space. Okay, so the coordinates that we have been talking about are 2D Euclidean coordinates, and we are unable to represent translation as a 2 cross 2 transformation in this space. So we will see what we can do about that, but please make sure that you understand this concept of linear transformations before we go there. So we will continue this discussion in the next lecture. Thank you.